Welcome! We are talking about the heart rate sensor today. So this small sensor, this breakout board, is able to detect many features about. Hello and welcome. We are going to be talking about the heart rate sensor today. This is an example of the breakout board that we're using. This is called the MAX 301005 heart rate sensor. It's also the SpO2, which is the pulse oximeter, measuring the oxygen level of your blood. There's many other kinds of heart rate sensors, other breakout boards, but this is the one from SparkFun that we're using. So we're able to measure heart rate, so pulse. We're able to measure your blood oxygen, as well as your temperature. All are measured with this one breakout board. It's best used for a finger or an earlobe. It's using red or infrared light, but we're going to use it on our wrist. Typically, the wrist-based ones do have green light, which is why if you ever look at some smartwatches, like an Apple Watch, sometimes if you look at the bottom of it, you'll see a green light flashing. It has to do with the way it reflects through skin. So the sensor that we have uses built-in light that pulses on the skin, and it looks for a reflection based on your skin. And it uses that to measure the pulsing of your blood through your veins. The temperature sensor is a different thing. It's simply a temperature sensor. It's based on the skin touch. So this operates 3.3 volts, which is great for us. It uses I2C communication, which is something that we'll explain what it is in a second. It's basically a different kind of protocol. So the OLED uses SPI. This is different. It uses I2C. It's just a different protocol. So the nice thing about I2C is you can see pretty straightforward. It's only got 4 wires. So it's already easier to connect. And for the first time that we can see that it uses the SDA and SCL wires on the argon, which typically we would think of as digital 1, digital 0, but we can actually see they are SDA and SCL. So kind of pulling back, this is a serial synchronous communication protocol, just like SPI. So it's a very similar graph that we had before. As you can see, you have a clock signal. The clock is kind of like the metronome. It's kind of ticking, 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 and it's saying this is the rate at which we're communicating. And so upon every clock tick, there is a data signal being sent. And so you're going to measure that, or the device is going to measure that at these certain frequencies. And that's basically how this I2C or protocol works. So particularly it's called the integrated circuit protocol. Again, it's serial, meaning one bit is sent at a time. It's synchronous, meaning it's clock-based. So there's a clock that's kind of setting the frequency. We like it because it has 2 pins. This makes it a little bit easier to use than all the OLED SPI wirings. Again, SDA stands for the data, so it's like serial data. And then the SCK, or SCL, depending on how your device is labeled, is the clock. Just as a quick note, like why would you think about why are these 2 different protocols exist? Well, there's actually multiple ones. There's also one called one wire. So just to show you, the I2C, right, its advantages are that it uses 2 wires, so it's already easier to deal with. It also uses more power, though, than SPI. So in terms of batteries, that would be a concern, because it's going to use more battery power. It's also a little bit slower than SPI. So that's also another downside. On the positive, though, it is sort of standardized, meaning I2C means the same thing in most places, where SPI does have variations depending on what version you're talking about. So this is what we're going to use to connect the heart rate sensor. So the library that we're going to use that's argon compatible is called the MAX 30105. I just wanted to walk through a little bit of how we might set this up. So pretty straightforward. We're used to this. We include the library that we've downloaded. There's also this extra wire library, which just allows extra support for the library that it needs to do its job. So we include both of those. We create a sensor object. Now, in the initialization, what we're doing is, this is kind of code from the library. This is essentially telling us if the code cannot find the heart rate sensor, right? So this is if this dot begin, if it fails, then the program immediately stops. So we'll never get out of the setup. It's got this infinite while loop. While 1 basically is like while true. So this just means if we can't find the sensor, don't progress any further in the code. Okay, if we can find it, then what we do is we configure the sensor, it's default settings. We turn the red light on. This is a trick we just use. Turn the light on so that it's always on so you can see if the sensor is working. So it's just a diagnostic tool. And then we enable the temperature that we want to be reading. And then we're ready to go. Now, once the program is running, we can take different measurements from the device. And we'll discuss later how you have the algorithm to actually register when a heart rate and show it that, but just at a basic level, we're able to get different readings from the red, the green, the IR sensors. Again, red IR typically are used for earlobe, fingers. Green is often best for wrist, but we can experiment with each one. So you simply call the sensor, get the reading value. If you want to get the temperature, it's pretty straightforward. We just call the read temperature function. It'll take care of that, or read temperature F for Fahrenheit. And then the process of actually determining, based on the value of the sensor, if a heartbeat was detected, is a fairly complicated algorithm. And so, thankfully, the library provides us a really simple method that we can use called check for beat. So when you want to check for a beat, right, so on some kind of recurring loop, we can measure whatever color sensor we're looking for, IR, green, red, and then we call the check for beat. And true or false, it'll give you a reading. And we can then decide if that beat's above or below a certain threshold, which would tell us maybe if the reading was valid or invalid, and we can then register it from there as we need to.